welcome to this session. This is Long Li. I'm a software engineer with Microsoft. Today I'm going to talk about how we implement SMB Direct for the Linux SMB Client. So agenda of this meeting is that first we're going to introduce the SMB Direct and the general programming with RDMA. Then we're going to talk about how we implement this SMB Direct, including the send and receive and the RDMA read write through the memory registration. And then we're going to look at how we do profiling and optimization to the code and find contentions and just make things better. Then lastly, we're going to look at some benchmark data we have this in this implementation. So first, so this work is based on the Linux kernel client. So there are a couple of Linux clients around for SMB client. The work is based on the sift.ko, so which is the Linux kernel client for SMB. So in the Linux, you can just mount CIFS when you want to do a SMB server access, and it will mount the file system just like any other file system on the Linux. It's all in the kernel space. So what is SMB Direct? SMB Direct is just a protocol for transferring the SMB packets over RDMA. Because it's working on RDMA, that means it works on all the transport supporting RDMA. That includes InfiniBand or Recv or IWAP. So it doesn't care about what kind of underlying transport it has, as long as it supports RDMA. It's first introduced with SMB 3.0 in Windows Server 2012. Then in 2012 R2, SMB 3.02 was introduced. Then lastly in 2016, and we have SMB 3.1.1. So in terms of this implementation, we really don't care about the difference between those three. The only thing we care about is the SMB 3.0.2, that where the remote invalidation was introduced. With that one, we can see that it requires some change in the code to deal with remote invalidation and speed up the RDMA process. So on Linux, actually you can do RDMA programming from both user space and the kernel space. They use different verbs. So in the kernel space, we are looking at the files in drivers infiniband.core, and the verbs you're going to be using is ibcore in ibcore. So although it's possible to do a RDMA connection just through verbs, and sometimes people find it's easier to use connection management, because that would be it's much more easy to use when you want a connection to the peer. And then people are wondering why it's called InfiniBand in kernel. This must be maybe legacy reasons. Maybe InfiniBand was first introduced with RDMA, so all the RDMA verbs will start with IB. That's what it was designed for InfiniBand. It first designed for InfiniBand. But RDMA transport can work on all the RDMA transport. That includes InfiniBand, Recv, and IWAP. So when you do RDMA programming, you may see some verbs or some flags. They have InfiniBand traces there. So you can specify something that is specific for InfiniBand. So when we implement this SMB Direct, we avoid using those verbs or these flags. Just make sure the implementation can work with all the RDMA transport, not just InfiniBand. So when you think of SMB Direct as a transport, I like to compare it with a TCP socket. They sit at the same layer in the kernel. So at top we have the user work IO load, and then when the IO data actually goes to the kernel mode, we have VFS, and then the sift sits below the VFS, and we interact with the virtual file system. Sometimes we interact with page caches to do the cache in the memory. And then below, we have the transport to the sift, so we have the same layer of a TCP socket. because there's so many similarities between SMB Direct and TCP, and I want to compare those two in the following slides. So when you transfer data with SMB Direct, you can actually do it two ways. The first way is to RDMA send and receive. Now this is very similar to TCP socket, with the only exception that there's no data copy involved. So when you run send data, you just send something to the RDMA layer, and then RDMA just send it, but with no data copy. The second way to do RDMA I/O is through the RDMA read and write. This is more interesting because in RDMA read and write, the CPU isn't actually involved in any I/O. The hardware is doing all the hard work. So that means the CPU can do other things while the I/O is taking place. So in the SMB Direct, we are going to use both ways to transfer data. So second, SMB Direct is connection-based. This is also similar to TCP/IP. To TCP. In SMB Direct, one RCQ pair is created per connection, and a completion queue is used to signal I/O complete. So in a way that why we use RC is that because RC is always reliable and it's always in order delivery, and that will simplify the protocol significantly when the I/O is in transit. So when we look at the RDMA send and receive versus TCP, and there are so many similarities, they both have the option to establish a reliable connection. In fact, SMB Direct itself is a reliable connection. So that means that everything is reliable, of course. So for the port number, it's the same as TCP port number. It's 445 on InfiniBand and Rocky environment. So that means when you want to connect to the peer, you just open port 445 and do a connection. It's the same as TCP. But on IWAP, the port number is actually a little different. It's 5445. Anyway, if you use 545 on IWAP, you get a connection. And in both cases, you are getting a reliable connection. But there's one major difference between the RDMA and the TCP. So TCP is stream-based. That means the application is working with a stream. So there's no boundary when you send data or receive data. Because you are working with stream, you need to figure out where the boundary is. So the application should have some way to figure out when the packet ends or when the packet begins when working with TCP. But for RDMA, everything is sent as datagram. That means the data is either sent as a whole unit or nothing is sent at all. So in this case, the transport layer need to figure out how to send this down the wire that is suitable for the hardware. For example, if the hardware is only capable of sending that much of data, the product stack need to figure out how to break those into small pieces and send over the wire. And then on the receive side, of course, you have those segments and you do reassemble those back and pass to the upper layer. So another major difference between TCP and RDMA is that in RDMA, the memory management is done by the application. So in TCP, you just send data and receive data and allocate your own buffers. The TCP will buffer all the IOs along the stack, so you don't need to worry too much about the buffer after being used by the transport. But for RDMA, the application manages its own buffers. That means things are more complex. So for example, if you send some data to the remote, and the remote doesn't have any buffer to receive this send, then we have a problem in RDMA. So for this reason, in RDMA, we need to carefully manage how the buffer is used by the transport. That's why we have a flow control system in SMB Direct. SMB Direct uses a credit system that's similar to the upper layer SMB protocol. You can only send data when you have credit. If you don't have credit, then you cannot send data. So here is what happens in SMB send and receive. On the SMB client, the data is passed to the SMB Direct layer, and then depends on how large the data is broken into smaller pieces, each less than the MTU of the underlying hardware. And then data is transferred over the SMB server. On the server side, this data needs to be reassembled and back to the original payload. So data is getting recreated by the reassembled, then the data is passed to the application, which is the SMB2 protocol. So in this case, also data is broken into pieces, but there's no data copy involved because SMB layer never copy data. So that creates some problems. Because we have to do the packet segmentation and the reassembly. That seems not the most efficient way to do that. In today's TCP hardware, this is actually done by the hardware in most cases, by offloading the TCP segmentation and the reassembly to hardware. But if you use RDMA send and receive, the software stack is doing all the work. That may not be the most efficient way to do it, especially for large packets. And then the test will show that if you do this for RDMA packet that is big, for example, 1 megabytes, it's actually slower than TCP layer because software is doing all the work that hardware should be doing. So that's why in SMB Direct, the send and receive is only used for smaller packets. Normally we set this size to be 4K, which happens to be 1 page in the memory. So any I/O size smaller than 4K or 1 page will be sent through the RDMA send and receive. And how about the packet larger than that? Then we have another way to do that. We'll look at that later. So we talk about the credit system used by SMB Direct. Now this is especially important for RDMA because if you send some data to the server and the server doesn't have a buffer for that data, then the send will fail. So we shouldn't send this data in the first place. That's why in the implementation, all the buffers are limited on both client and server. So client server should have some way, somehow figure out how to send data and how to not send it. Not send it is more important to send it in this case. So in SMB Direct, the credits is embedded in every protocol message. In fact, they are the first 2 fields in the protocol header. And that allows the client and server to exchange information about how many data can be sent and how many can receive. So they use this credit to decide to send to the peer or not. Because in RDMA, if you don't have buffer, the sender will fail. So this credit is very important. If the credit fails, then you will see failures on the wire. Okay, so what about the client sending a lot of data to the server and then the client running out of credit? If the server doesn't give the client any response, the server won't have a chance to tell the client that it has allocated more buffers and available for more receives. So in SMB Direct, this problem was addressed with packet without payload. So it's just an empty packet. The purpose of empty packet is not to transfer data, it's just extend credit to the peer. So the server saying that it has allocated new buffers for the transfer. So the client can keep sending more data. So in practice, the SMB Direct packet without payload is heavily used because in heavy traffic, you need to extend the credits as soon as possible. So in the actual I/O load, a packet without payload is processed, as we can see later, is processed in another queue, in another CPU to speed things up. So how about large packet for file I/O? Because we don't want to do SMB send and receive in those cases. We don't want to break the I/Os into smaller pieces. Typically, SMB negotiate I/O size is 1 megabytes. So for 1 megabyte I/O or larger I/O, we have another way to do it, which is RDMA read and write. In RDMA read and write, the data is no longer broken into smaller pieces. So we don't need to care about how the data is broken into and reassembled. We just need to send a single packet to the server. That packet is the protocol headers that says the server wants to access this memory through RDMA read or write. So after the server gets that packet, server will look the information in the packet and locate that memory region on the client, and then do a remote server-initiated RDMA read. In this case, it's RDMA write, SMB write, so the server will do RDMA read to that data. So when the server is doing the actually RDMA read, the client actually doesn't know about that because it's done by the RDMA hardware. So CPU can do other things at the same time. But in this case, we avoid the fragmentation, and so the data transfer is more efficient.
So assume the lower packet is, of course, a send receive version, not a write, right?
So for smaller packets, we use send and receive. The reason we'll explain later that is because when you do RDMA read and write, there's a cost of doing memory registration. So sometimes the cost of doing memory registration outweighs the cost of doing packet segmentation. So in this case, you need to figure out the correct packet size to do read, write, or to send or receive. So now we come to the memory registration. In order to do RDMA read and write, the memory has to be registered with the hardware. So this process is called the memory registration. Memory registration, RDMA hardware, because it's hardware, so it doesn't understand the virtual address. In memory registration, we just use pages, and then the I/O data is also described as pages. The memories is mapped to hardware address, and then we set up correct permission on the registration set. Its memory can be read or write by the kernel, by the server. And then after memory registration is done, the client needs to pass this information along to the server by RDMA send or receive. So how does the SMB client send those information to server? It's in the SMB2 protocol. For example, in SMB2 READ, we have the channel field. In the channel field, the client can specify if this is normal SMB channel, or is using RDMA, or is using RDMA with invalidate. So if the client is using RDMA or RDMA with invalidate, that means the actual data is not in the packet. In this packet, it's in another location in the memory. The server will look into this field. If it figures out this is RDMA read or write, it will look at the buffer at the end of the SMB read. Now the buffer is no longer data. It's a description of the data in the client memory. So the buffer has offset, token, and the length, and which describe the location of the memory in the client. So we need to figure out how to pass the information from InfiniBand, from RDMA in Linux to the SMB server. So here is the memory registration in the Linux. When we register memory, we have this structure to describe the location and the permission and something like that. So in this way, we just copy the remote key to the token. Remote key is the key that in the RDMA layer that tells the peer how to access its local memory. That has been mapped. Then the IOVA is actually the offset. Personally, I think the name is a little confusing here because IOVA seems to indicate the hardware address of this memory registration. But in the SMB Direct, it's offset. So anyway, we can just copy those values along to the SMB Direct buffer. Then the server will understand how to locate the memory registration in the client and do RDMA read or write. So there's a cost with the memory registration. Because when we do the RDMA I/O, we have to make sure the memory is fully registered before posting the request to SMB server. Now the registration can be done through IB verb. When the IB verb returns, the memory is registered. That may involve some time, or even a context switch if we have to wait for completion, and if the verb is blocked. Or we can use another way, it's called the FRWR, Fast Registration Work Request in Linux. So this is a little different to using a verb to do a memory registration, in that we send a memory registration work request to the queue pair through IB post send. Now we don't need to wait for completion, or we don't need to call schedule again. We can just proceed with sending the next SMB request packet to the queue pair, to the server. So this memory registration work request acts like a barrier in the queue pair. The hardware guarantees that this work request we are finished before the next work request. So that's guarantee us that the next sending request will get to the server. By the time it gets to the server, the memory is already registered. So we are safe here. So now we have finished I/O. And then this is something we need to do after I/O is finished through memory registration. Before we pass the I/O along to the upper layer, so upper layer can consume this I/O packet, we want to make sure the server can no longer access this I/O. This is done by doing a memory registration invalidation. This is important to do that because you have to make sure the server can no longer write to this I/O region after the I/O is done. So invalidate is done by posting a work request. It's called the WA local invalidate to the queue pair. After this work request finishes, server has no longer have access to the memory. So now we are safe. We know that server will no longer change the memory. So this work request has some cost because when you post something in the queue pair, the I/O thread has to wait until this finished before passing the data along. Now, if you wait here, there's a call to schedule. That means there's a context switch on the CPU. The context switch may slow everything down, which is not good for the RDMA fast I/O path. That's why in SMB 3.02, the server supports a new feature. It's called remote invalidation. By specifying remote invalidation, when server is doing an RDMA write to the memory registration, after server finishes that command at the hardware layer, the memory region is automatically invalidated. So we no longer need to invalidate that. So we can save some CPU by not calling schedule and wait for completion on that work request. So that improves performance. So the remote invalidation is supported on most hardware. So today's hardware, I don't know any one of those doesn't support remote invalidation. So this is probably safe to use in the SMB server and client. So now we are looking at how the memory registration is done in the SMB Direct. As I explained, when you do the memory RDMA read write, you need to register the memory and then tell the location to the server. Now in the kernel, you need to allocate a data structure to do that. It's called a memory registration structure. The kernel needs to maintain some of those memory registration. So whenever a new request comes in, the server can pick up a new memory registration and satisfy that I/O and pass it along to the server. So this has a problem. What happens when the I/O is done? What to do with that memory registration kernel just created? Need to destroy it and unmap all the hardware resources with the RDMA hardware. So this actually is a slow process to unmap all the pages from the hardware. It can slow down the I/O if not doing properly. So in the implementation, you don't want to really allocate those stuff on the fly. But that may also slow things down. So we actually maintain a list of pre-allocated memory registration slots. And then when the unregistration happens, so it's like when you have a lot of stuff to do in computer science area, you want to break those into small pieces and have other CPU do each pieces. So that's why we defer the memory deregistration to another CPU to do it, while at the same time, you may have I/O issuing process for another CPUs, and those can run at the same time. So in other words, the memory deregistration doesn't block any I/O issuing process. Also, if you look closely at this structure, because we have a fixed number of slots, and then all those processes try to access the same slots, the only thing they want to modify is the memory registration status, and they don't modify the links. So there's no lock for this memory slots. Because there's no lock, we don't have contentions when the I/O happening is when I/O process activity is high. There may be multiple processes try to access this list at the same time. So what's the benefits of doing RDMA read write? As we can see, the first benefit is the CPU doesn't need to be involved in RDMA read write. The CPU can do whatever it needs, where the data transfer is being done by hardware. If the busy server, that means CPU can do other things. That is always good. Another important thing is that in RDMA read and write, the hardware will figure out the best way to transfer data. It will do segmentation and reassembly if the MTU is less than ideal. But this stuff is being done in the hardware, so that means it happens fast. The con of doing RDMA read and write is that there's a fixed cost of doing memory registration and invalidation and deregistration. So that's the reason we don't want to do that for very small data. That may not be the best way to do it. Maybe you get fast speed, just send those data to the remote along instead of doing memory RDMA read write. So the default threshold we choose is 4K bytes. Anything less than 4K bytes, the I/O payload is being sent by RDMA send and receive, and anything bigger than that is being done by read or write. So because the RDMA stack is usually designed for fast speed, and when you design some software work with speed, you need to figure out how fast the code runs on certain code paths. You need to identify which part is slow and which lock has high contention, so you can start to optimize. So in terms of profiling, so different people actually approach this differently with some tools, kernel prof tools. So I found the best luck of writing my own little profiling code. So there's a register is called timestamp counter in the Intel-based CPUs or AMD CPUs. There's one for each CPU. The hardware maintain this TSC. When there's a hardware cycle, this one is increased. So the TSC is equivalent to the CPU cycle. And there's an assembly command to read this on Intel platforms, which is read TSC. It almost has no cost. So if the BIOS is properly configured, the TSC is pretty accurate for the profiling purpose. And then when you run a large data, you need to figure out how the code path is being is being run again and again, and you need to figure out the histogram of the time spent on those code. So I found the best luck of using another hardware command is called the built-in CLL, the number of leading zeros. Is another Intel instruction to count how many leading zeros in a value. And that tells you how large the value is. So I use this command to store everything in the histogram. Again, I find this very lightweight. It doesn't it can do everything about 20 CPU cycles. So this profiling is always enabled in the SMB Direct code. I don't see any negative impact of this profiling approach. So with profiling, we immediately find some issues with the code path. So look again, when we do a RDMA transfer, we send the data along to the server, and the server do a RDMA read-write. Then the server response came back. Now this response is interesting because when you get something back from another server, it's involved at least 2 CPUs on the local machine to do that, to pass the server along to the final I/O process. The completion arrives at the interrupt contact, but actually I/O thread used by SIFT is running on process context. So somehow we need to find a way to pass this data from the interrupt to the process. So look at it closely, and we have found that, of course, those are running on 2 CPUs. On one hand, we have 1 CPU in the interrupt. That is polling the completion queues for this queue pair. Of course, the CPU cannot be blocked because this CPU is handling all the completions on this queue pair. If it's blocked, then the queue pair may have some issue with this queue pair. So the queue pair needs to be polled as soon as possible. So on the other hand, we have another CPU, and it's running on the process context, and it's reading all the I/O data from CPU 1. So now we have 2 CPUs. The logical solution to do this is to have a queue. So CPU 1 can put everything on the queue when the package arrives at this CPU, while the other CPU read from the queue. When the queue is not empty, that means the data is there. So the other problem with this queue architecture, because when you have a queue with 2 CPUs, normally you want to use a lock. Maybe spin lock is your best friend. But in this case, it's not really your best friend because the test shows that the contention is high. It's probably because that the CPU 1 always has some data coming in, and at CPU 2, it's always try to read something. So they always try to grab a lock on the queue, and there are always something in the queue all the time. So we don't want to really use a lock here. So if you look closely at the queue, CPU 1 only add the packet to the end of the queue. And the CPU 2 always read the packet from the front of the queue. So look closely at those 2 elements in the queue. They don't really modify the same data. When CPU 1 adds packets, it only modify the links at the end of the queue. And when CPU 2 tries to read something, it's only modify the links at the front of the queue. So with careful programming on this area, memory barrier can be used to reduce log contention in this case. In memory barrier, we just make sure the links are updated before the packet arrives. Then we still need a lock because in some situations the queue can be have no element or 1 element. The lock is still needed. But with memory barrier, the log contention can be greatly reduced. In other words, when the heavy I/O happens, then we don't see the log contention doesn't go up. So that's pretty good. And of course, the rim buffer is the best solution to this. A RIM buffer can just totally get rid of the lock by using memory barriers on all send and receive paths. But in this case, because we also need to deal with empty packets in SMB Direct, and those packet amount also can be huge. So we choose to use another queue to do empty packets and use another CPU to process those empty packets and get it back to the RDMA stack. That's more efficient than, so that's why I choose to use a linked list here to reduce and use memory barrier to reduce the load contention. Okay, another area interesting discovered by the profiling is that the send path is about 6 to 10 times slower than the receive path. So this is a problem I'm still working on. The reason for send paths being slower is that in RDMA, you don't do data copies. So when someone asks to send some data, you have to send some data and return it after the data has been sent. The return it also means that the other end has received it. So this process can take some time. So if you look at the SIP code to send data, the SIP allocating its own buffer, and then call transport to send buffer. And after that, the buffer will be released. Now, if you use RDMA to do step 2, then we have to wait until I/O is finished, because the buffer is not ours, it's upper layer's buffer. Now this code runs faster in TCP/IP, because TCP/IP just copy everything to the TCP/IP stack, so we can quickly return from the step 2. Now for RDMA, because we cannot return, so this may take some more time and possibly cost schedule that slow everything down further. So the solution is to move the buffer allocation code to the SMB Direct layer. So SMB Direct, we allocate all the buffers, and we keep accounting the buffer usage when do the RDMA transfer. Then we can return immediately to upper layer after the transport is called to send the buffer. Now this work is still in progress because it involves a lot of changes. But from the experiment, I estimate about 5 to 20% performance improvement on high queue depth situations. Okay, so here's the progress of doing this SMB Direct work. The patches has been submitted to the kernel's mail list upstream. To try the patch, you just mount, do a normal mount to SMB server. Just specify RDMA in the mounting options and specify SMB version that it supports RDMA. Then the direct layer is designed to have a lot of logins and profiling, and also kernel messages to help debug. We're still in the early process, so we need to figure out when something is going wrong. Okay, so here's some test data we have done in the lab. So keep in mind, this is a very early stage of the experiment, so the data is very highly experimental. So for this test, we use 40G InfiniBand on both server and client. And the SMB used is SMB 3.02. So keep in mind it's 40G InfiniBand. That means the line speed will be 32G. So here is the read throughput. Different colors of lines represent different queue depths. So as long as you can see, as I/O size goes up, we have better throughput. And then the peak has to reach at 16 queue depths. And as you increase more queue depths, then we don't really get any further than that, from 16 queue depths. This is SMB read, and the other one is SMB write. SMB write is a little behind SMB read, for the reason I just described, we are a little slower. I think maybe the reason that we're a little slower on the standard path. Another reason may be in the current SMB client, we really don't support multiple queue pairs. So if we use multiple queue pairs, things may improve. So all the tests has been done on a single queue pair on a single SMB Direct connection. So what happens if we use multiple queue pairs? Oh, by the way, just for the curious, so we pick about 3.5G in read and 2.6G in write. These numbers for Windows are 3.7G for both read and write. So we are still a little behind Windows, but for read we are about 85% of the line speed of the hardware. Now let's look at how what the effect is if we increase the number of queue pairs. As Windows supports multiple queue pairs, so the ultimate goal is to have multiple queue pairs, multiple connections in Linux. So with multiple queue pairs, this is just simulation. I use the same, connect to the same tree, and then do the I/O benchmark on two files, simulating that if we have two queue pairs, we're going to same speed, hopefully. So after multiple queue pair is used, you can see the read performance is the same. It's probably because we have reached the line speed. But for write, things get better. We can get about 3.5G, about the same as read. Okay, so here's some future work I'm planning to do. And first is to allocate all the buffers for SMB Direct, so we can use non-blocking cores for all the lapo layers that should speed things up. Then it's the multiple channel support. Hopefully that will also speed things up. Questions? Yes.
You mentioned there's a different queue for empty packets on receive. Empty packets should be pretty rare. Do you ever get any of them?
Yes. So it's if you're running a 2K, for example, 2K packets, you don't do RDMA read write. You do send and receive, and almost every time you send two packets, and the other side need to.
A very credit-intensive workload.
It's very intensive. It can happen. In that case, it's about half of the packets are empty.
Really?
That's.
We should look at the credit management. It should be rare, even in a very busy traffic situation.
Yeah, I find out.
A credit can be granted and requested along with a data-containing packet. So in other words, if you have empty packets, it means you're not sending a data packet.
So my wording is not accurate. I'm talking about the empty packets from the client to server. Those packets are sent, then after they're finished, they go through the same code path because they complete on the same queue pair.
Yeah.
So I'm talking about those empty packets, not the packets from the server to client.
Yeah. Same thing though. I mean, it's a
maybe
it's a symmetric relationship between the two.
Maybe,
so there may be some oddity in the credit management.
Maybe it's too active.
Maybe.
Yes.
Are there any changes required in the overhead stack to make this work?
No. So it works with standard RDMA stack, in-kernel RDMA stack. There's no change for any other code other than the SMB code. Okay, thank you for coming here. I hope you enjoyed the talk. Thank you.